Welcome to Advent of Code 2022. This is day 15, over halfway through. I've been enjoying it. If you guys are enjoying it, drop a like. I appreciate it. And let's get started. The beacon exclusion zone. You feel the ground rumble again as the distress signal leads you to a large network of subterranean tunnels. You don't have time to search them all, but you don't need to. Your pack contains a set of deployable sensors that you imagine were originally built to locate lost elves. The sensors aren't very powerful, but that's okay. Your handheld device indicates that you're close enough to the source of the distress signal to use them. You pull the emergency sensor system out of your pack, hit the big button on top, and the sensors zoom off down the tunnels. Once a sensor finds a spot it thinks will give a good reading, it attaches itself to a hard surface and begins monitoring for the nearest signal source beacon. Sensors and beacons always exist at integer coordinates. Each sensor knows its own position and can determine the position of a beacon precisely. However, sensors can only lock onto the one beacon closest to the sensor, as measured by the Manhattan distance. There is never a tie between where two beacons are the same distance to a sensor. Okay, that's good. Manhattan distance is grid distance. So you take the diff of the x plus the diff of the y. That's or ABS x1 minus x2 plus ABS y1 minus y2. It doesn't take long for your sensors to report back their positions and closest beacon. Your puzzle input. Let's copy this guy real quick. Ample. And while we're copying, we'll copy the input. So right away, noticing that the difference between the input and the example is just the size of the x and y numbers. There's really not that many more sensors. So consider the sensor at 218. That's the first sensor here. Its closest beacon is at negative 215. For the sensor at 916, its closest beacon is at 1016. Okay. Yeah, is that absolute position? I guess so, right? Not relative position. Drawing sensors as S and beacons at B. The above arrangement of sensors and beacons looks like this. So, yeah, where's the 218, right? 1, 2, 18, or maybe it's 0 to 218 here, and its closest beacon is negative 215. Yeah, okay. All right, sure. This isn't necessarily a comprehensive map of all the beacons in the area because each sensor only identifies its closest beacon. If a sensor detects a beacon, you know there are no other beacons that close or closer to that sensor. There could still be beacons that just happen to not be the closest beacon to any sensor. Consider the sensor at 87. Right, so using Manhattan distance, this beacon is the closest one, but that means there's no beacons in this area, okay? Sensor's closest beacon is 210, so you know there are no beacons that close or closer. None of the detected beacons seem to be producing the distress signal, so you'll need to work out where the distress beacon is by working out where it isn't. For now, keep things simple by just counting the positions where a beacon cannot possibly be along just a single row. So, suppose you have an arrangement of beacons and sensors like in the example, and just in the row where y equals 10, you'd like to count all the number of positions where a beacon cannot possibly exist. The coverage from all the sensors near that row looks like this. Okay. In this example, in the row where y equals 10, there are 26 positions where a beacon cannot be present. Consult the report from the sensors you just deployed. In the row where y equals 2 million, how many positions cannot contain a beacon? Okay, so the example, we have we're going to use y equals 10. And for the actual input, we're going to do y equals 20,000. So input file. So when we parse input, we're going to parse the file name. And we're going to find y is an int here. And Okay, so we got to parse this line. So we're gonna do sensor data class sensor has a location. We're gonna do tuple int. Can you have labeled tuples? I just wonder. Python labeled tuple. Oh, they have named tuples. That's a collection. Okay, all right, so we're gonna do location is a named tuple of so you do class location named tuple, and you do x int, y int. Oh, I like this. This is nice. Okay, cool. And then we do location is location and for the sensor, and the beacon has a beacon. Beacon location. We'll just we'll call this a signal because we're coming back with a sensor location and a beacon location. Okay, and then each line is gonna be a signal, and we're gonna do signals. Cool, signals. So we're also gonna do y equals 10 if file name is example, else 2 million. And we're gonna do parse signal line, def parse signal line stir signal. Okay. Let's just do this. So we're just going to split on space and get the x, y, and beat the sensor XY and the signal XY, and then return signal sensor equals location x equals sx colon 2 colon -1. So starting at the third integer and going to the second to last, or third character, and we just cast that to int. All right, and then we do the same thing. Y has the same look, so int sy 2 to -1, and a beacon equals location x equals int bx 2 to -1, y equals int by 2 to actually 2 to the end, because this doesn't have a trailing character like a colon or a comma. Okay, so that returns our signal. That should be good. Let's print our input here. Just make sure we did it. Python day 15 example. Yeah, 218, negative 215, and then y here is 10. So that's cool. And then actually let's do it for the input. And we get much larger number still working, and y equals 2 million. Cool. Input is red. All right, so to just walk a single row, we just need to count the number of positions that cannot possibly, that basically if they're covered by a signal, right? So I want to make a helper function def is covered by a location. So if it's covered by this signal, right? If it's in between, if it is part of this this diamond created by the sensor and the beacon distance. So property def Manhattan distance. So the Manhattan distance is the ABS of beacon.x minus sensor.x plus ABS of beacon.y minus sensor.y, and is covered we take that distance and we look at the distance to, actually what we want is this function to be outside of signal. Sorry, because we want to call it on arbitrary locations. And we're going to do L1, L2. Ooh, right? We could put it on location. That looks good. All right, cool. So we have a Manhattan distance, and then we want to do, we could do it as the subtraction, but I don't remember how to do that. So we're gonna do self.sensor.Manhattan distance to self.beacon, right? And then self.sensor.Manhattan distance to the other location, and basically it return this first one less than, so greater than or equal to the second one. Basically, if the beacon's Manhattan distance is greater than or equal to the distance to the line in question, so if we're talking about this point, it has a lower Manhattan distance to the sensor than the beacon. So the beacon has greater than this. And if it's the same, then this returns true. So that means it is covered. And all we need to do is go through each sensor, go through each point, then go through each sensor and determine if that sensor covers that location. So and I guess we need to determine the bounds of x. So min x equals min of sensor, so s.sensor.x for s in input.signals And we need to do s dot beacon dot x for s in input dot signals. And we need to get the min x and the max x. And that'll determine the boundaries of x, right? Well, how do we know how far to go in X land? Okay, so we just need to determine how many positions where it does cover. So we can only cover we need to determine the farthest reach that any signal has. So I'm going to make a function that says def farthest x, or min covered x, self int, and this is going to give us the minimum coverage of x and the maximum covered x. And it's actually pretty simple. Return. So we get this Manhattan distance. And so the covered x is sensor.x minus self.distance sensor.x plus self.distance. And what this is going to do is give us the x boundaries that this signal covers. We're going to use this to get the minimum x. So what we're going to do is covered x for x in covered x, but this has to come after. All right, so now we have our boundaries of coverage, and we are going to use that to measure. So then basically return range of min x to max x plus 1 dot filter, or we'll do sum of 1 if for x in range min x max x plus 1. All right, so we're going to go through each x and we're going to say for signal in input dot signals if covered equals 0, if signal dot is covered, and we're going to do location x equals x, y equals input dot y, covered plus equals 1, and then continue, or actually break. We want to break out of this for signal and input signals, and then return covered count. Now, There's probably going to be a lot of numbers in the input case, but I think because it's just, there's only like 20 signals, it's just O of n. So it should be good to run. Method is not iterable. Oh, right. 27. That is incorrect. Are we counting this beacon? -2, 0, 3, up to 24. Oh, I guess we're not counting the beacon. Okay. So yeah, we'll get the beacons, which is a set of location, equals s.beacon for, wait, why can't it? Oh, counting the positions where a beacon cannot possibly be. You know what? Let's just do beacons. We'll count signals and beacons on the row. So cannot cover equals sum of signals on row is sum of 1 if input dot if s dot sensor dot x equals dot y equals input dot y, else 0 for s and input dot signals. We're going to do the same thing for beacons. And then we just return covered minus beacons on row minus sensors on row. And this will give us 26 for the example. Now it's giving us 24. Wait. Let's look at the example. We're looking at y equals 10. There are 3 beacons at y equals 10, but they're the same beacon. All right, okay, all right. All right, so now we're using a set to do this, doing the same question, but now we're just going to do taken spots. And minus for int inset. 26, okay. And input, does this run quickly? Maybe not. Let's just do a quick TQDM. See how long it's going to take. Okay, this isn't going to take forever. It'll be done in a second. We can think while it's running if there's a better way to do it. I mean, the problem is that we have to go 7 million wide. So instead of taking a big chunk. So I bet this works, but it will not be good enough to go the whole problem. So it does work, but we're going to have to be smarter about part 2. Your handheld device indicates that the distress signal is coming from a beacon nearby. The beacon is not detected by any sensor, but the distress beacon must have an X and Y coordinate no lower than 0 and no higher than 4 million. Okay, so, we did go over 7 million values, but now we have to go over 4 million by 4 million, which is going to be much harder, or we have to be much smarter about it because we do not have time to wait for that. To isolate the distress beacon signal, you need to determine the tuning frequency, which can be found by multiplying X coordinates by 4 million, then adding its Y coordinate. Okay. In the example, so let's just start by writing that function def tuning frequency self property return self.x times 4 1 2 3 4 5 6 plus y self.y. Okay, so we wrote that. In the example above, the search space is smaller. Instead, the x and y coordinates can be at most 20. With this reduced search area, there is only a single position that could have a beacon, 1411. The tuning frequency is this. Okay, so we're going to have to be a lot smarter. So we'll start with just some management stuff. So bounds equals min x equals 0 and min y is 0, but max x equals the input. The maximum y is input.y times 2. So max y equals input.y times 2. All right, so it's either 4 million, 2 million times 2, or 10 times 2. So we have the max y and max x, max xy. It's the input.y times 2. All right, so now we need to be much smarter about this. And we need to find, because we can't just run through every single position in the box and see if it's covered. Because we have 4 million by 4 million coordinates to run through. And you can't do O of n squared of 4 million. So I'm going to think for a bit about how to speed it up. First of all right, let's just write the naive solution and start it running while we think. I mean, that can't hurt, right? And basically, if it's covered, then we break immediately. And we just return immediately if this position is not covered, and we return the location x equals x, y equals y, dot tuning frequency. And if we run this on the example, it comes back really fast. Yep, that's the right answer, but on the input, it's going to take a while. Wait, it's not actually taking that long. Oh, but because it's still running part 1. So what we're going to do is return -1 immediately, so that because it takes a while. And yeah, so part 2 is taking a very long time. So we need to be smarter about it. So what we could do is create a 4 million by 4 million matrix that contains a map of all the coordinates, and we go through each signal and we map its diamond shape onto the matrix. And that would take basically O of n squared, n is 4 million, times the number of signals, which is like 20. But it'd be a little faster than checking is covered for every single one. Another thing we could do is that we could make this check smarter. So we could start on each row, and we start with y equals 0, and we go through each signal and we look for the coverage. And when it's covered, we actually check, okay, how many y's are covered, and then we just increment by that, and we go to, and then we start over. And once we get to the end of the line, we start over, right? So that actually sounds like it'll speed us up quite a bit. So I'm going to try that. So I'm going to create a new function called def y next y uncovered self, and we'll take the location, and we're going to return a location. So first we check basically if it is covered, if self.is covered y, or if it's not covered, then return y. And then if it is covered, we basically want to increment, not y, sorry, look. We want to increment the location by the difference in distance. So return location, look.x equals look.x, and y equals we're just going to do the calculation here. D equals this. Self.distance is greater than or equal to D. then we do self.distance. We do loc.y plus self.distance. So if it's all right, let's think about this. So if we're talking about, so if we get to this y, the distance is 1, 2, 3, 4, 5, 6, 7, 8. It's 9. And we want to move it to here. So we take so this would be well, I guess we're moving down, but it doesn't really matter. So this would be -9, and then we need to add so we need to take 9 minus -9. So then we do y plus self.distance minus y diff. And that should give us the next location that is uncovered, right? So if you consider x to be, so all right, so if we have this, oh, but we need to remove the x factor. All right, so if we get here, then we need to add 1, 2, 3, 4, 5, 6. And the x factor is 1, 2, 3, 4, 5, 6, 7. And the total is 9. Oh, this is hard. Sorry. Okay, I'm just trying to figure out how to increment these. Well, let's just start with this one. Okay, so we're at -2. The sensor's at 7. So 7 minus -2 is 9. So the y diff is 9. The x diff absolute value is going to be 0. And the distance is 9. And we need to add to get all the way to 17. So that's going to be plus 18 plus 1. So we need to do new y equals, or y factor is going to be the self.distance minus the y diff. But we also have to handle in the x diff. So we're going to add 1. But all right, so but if we're here, we need to go -1 to 16. And so we need to add 17. So we take the we actually want the self.distance minus the x diff ABS. So that's the distance part of the y, like y target equals self.distance minus x diff ABS. So in this case, you know, this is the y diff here is going to be 8 and the x diff is going to be 1, or it's actually going to be -8. And then so 9 minus 1 is going to be 8. And then we're going to have 8 y target minus y diff plus 1. Okay, so that's what we want to put in here. All right. So then let's test this on well, we can just test it here. So we start with y equals 0 for signal in input.signals. So we do while y is less than max xy, less than or equal to, for signal in input.signals. If signal y equals signal.next uncovered, next y uncovered. And I guess we have to do covered equals true. Signal dot is covered. Look. And then we break. So basically, all right, so we're going to start with x, y equals 0. While the y is less than the max xy, we're going to set covered to false and go for each signal by. And if it is covered by location, we're going to set covered to true. We're going to set the location, we're going to increment the location to the next y that's uncovered, and then we're going to break. And because covered is false, this will not trigger. And then if we get a location that is totally uncovered, then covered will still be false when it hits here, and we will return that location. It's tuning frequency. Okay. Okay, it still works for the example. And we're actually running on the input. Okay, so that's cool. Like, this was a good slight improvement. It avoids us having to walk all of this 4 million by 4 million matrix, because like so we only have like 20 signals, and they cover 4 million times 4 million minus 1 spots. So they're very wide, these covered zones. So when we get the next Y that's uncovered, we're moving huge amounts. So probably, running, let's see, we're still going one by one on the X. So we're running 4 million times like 20 operations 20 times. So 4 million times 20 times 20, which is much faster than 4 million times 4 million. So I'd expect to get an answer soon. And yeah, it's probably not the best. There's probably something that runs in linear time, but you get what you get on the day. You solve it the way these videos are me solving it actually. Like you're not watching some prepared solution. Okay, well that's bad. It didn't find something that was uncovered. So we did it wrong. All right, well, let's keep thinking. All right. First of all, we're only calling next y uncovered here, so when it is not covered, so we can just assume it's always covered. Let's just check a few extra cases here. Like, what if our location here is x is actually on the sensor? So we have a beacon, we have a distance of 9. So the y diff is going to be 0, the x diff is going to be 0, and the y target is going to be 9 minus 0, so 9. And then we're going to move the y location, so 7 plus the y target is 9 plus 1. So that would land us right here, which is exactly what we want. So that's actually correct, y target minus y diff. So any point along here would actually work, right? And let's just say it's on this beacon. Well, the x diff here is, this is 2 to 8, so 6. So that's going to be 6. And the y diff here is 10 to 7, which is positive 3. And the distance minus the x diff is going to be 9 minus 6, equals 3. So then we're going to have 3 minus 3 plus 1. So it'll only move 1. So I think next y uncovered is correct. I wonder what else we're doing wrong. So x is running through 0 to max xy in the 4 million by 4 million plus 1. And we are checking the location of y. So let's just print moved y to, well, and let's have a signal. Let's do sensor I Okay, here's a problem. That's cool. So this was my suspicion, right? Why is sensor 1 moving a location multiple times? That should never happen, right? The idea of calling this function is that it moves it once. So let's run it on the example and see if we have the same thing. Yes, we do. Okay, so sensor 2 moved location 14.1, 14.3, and 14.7. All right, sensor 2 is, so sensor 2 is this sensor, right? So x13, y2. Let's go up to our next y uncovered, right? And our location, so 13 and 2, whoa, sorry. Make this smaller again. All right, so 13 and, make sure it's not covered by my face. All right, 13 and 13, 2, 15, 3. So 13, 2, 15, 3. So distance here is going to be 3. All right. So, and we're looking at location is 14.1. Okay, so D, censored on Manhattan distance to location, so is going to be 2. The X diff AB absolute value is 14 minus 13, absolute value is 1. The Y diff is going to be 2 minus 1, which is 1. Oh, this should be -1. Oh. All right, let's try that again. Okay, now we have no repeated sensor movings. We still get the right answer. Let's run it on the input, and it'll actually run faster now. Because we'll have less repeated movings. Okay, so hopefully we get an answer this time. Yeah, I mean, I think that bug, yeah, that was just basically what happened was so I was calculating like we were doing, okay, this is -9 to here, but actually this was, if you were here, it thought you were here because it inverted this Y coordinate. So let's see, halfway through the matrix almost. And we can use this same strategy on part 1 as well. That would make part 1 fast. Ah, we got a number, yay. Yay, we got it right. Okay, so cool. We had a good improvement and we introduced a bug and then we figured out the bug pretty quickly. So yeah, thought this problem was pretty good. We didn't make it fully linear time. So I might check around some other people's solutions and see what other people did. Maybe they did it better. Who knows? But I'm happy with our answer and I hope you guys enjoyed the video. I'll see you next time. Peace.